In this video, we will talk about torque. Try to rotate a door by applying a force of constant amplitude and perpendicular to the door surface at 3 different distances from the hinges. You will find it easier to rotate the door by applying the force near the door handle at point A than by applying it between the door handle and the hinges at point B, and you will find it more difficult when you apply the force near the hinges at point C. Now, if you try to rotate the door by applying on its handle a force which is parallel to the imaginary axis delta passing through the hinges and called the axis of rotation of the door, you won't be able to rotate it regardless of the chosen direction of this force. And if you try to rotate it by applying on it a force whose line of action intersects the axis of rotation delta, you also won't be able to rotate it regardless of the chosen direction of this force. To formalize this concept, we define a physical quantity denoted by the Greek letter tau and called torque or moment of a force as the tendency of that force to rotate the body to which it is applied. Therefore, the torque of a force F about an axis delta is equal to 0 if F is parallel to delta or if the line of action of F intersects delta. Torque is a vector quantity. It is equal to the cross product R cross F, where R is the position vector of the point of application of vector force F relative to the pivot point, which belongs to the axis of rotation delta, as we can see in the figure showing a wrench used to rotate a bolt. Its magnitude is given by the product of F, R, and sine gamma or sine beta, where R is the distance from the point of application of F to delta. Gamma is the angle between the two vectors R and F, and beta is the supplement of gamma. This formula shows that torque is proportional to R and explains why door handles are placed the farthest possible from the hinges. To get the algebraic value of the torque, we remove the absolute value and we add plus or minus in the formula depending on the chosen positive sense of rotation. In the shaded right triangle, we can say that sine beta equals the length of the opposite side D over the length of the hypotenuse R, where D is called the lever arm and is the perpendicular distance from the axis of rotation delta to the line of action of the force F. This leads to R sine beta equals D. By replacing D by its expression in the formula of the torque, we get the torque of F about delta equals plus or minus Fd. In the international system of units, F is expressed in newtons, R and D in meters, and tau in Newton meters. Now let's define the couple as a pair of non-collinear forces of equal magnitudes and opposite directions. The torque of a couple F1, F2, where the magnitudes are equal to F, is given by the formula tau of F1, F2 is equal to plus or minus Fr sine beta, where R is the distance between the points of application of the two forces, F1 and F2, and beta is the angle between the line segment joining these points and any of these two forces. For example, the torque of a couple is equal to the sum of the torques of each force, since the tendency of a couple to rotate the body to which it is applied is the tendency of both forces to rotate this body. We start by replacing each torque by its expression while respecting the chosen arbitrary positive sense of rotation. Then we replace F1 and F2 by the common magnitude F and factor by F sine beta, and finally replace R1 plus R2 by their sum R to get Fr sine beta. And this is all for this video. Thank you for watching.